Hi folks, it's Matt again, and we're going to talk now about dominant strategy implementation. So the idea that we're looking at is we have a society, we have to make a decision, and we're trying to design a mechanism that is going to take people's preferences and give us outcomes. And in particular, let's start by looking at a situation where we've got a full set of alternatives and any possible ranking over those things. So for instance, we have a set of candidates that we need to pick from. Say 4, 5, 6 candidates. Okay, so we think about the voting rules that we looked at earlier. Now we've got to make a choice over these candidates, and in particular, what we'd like is when we ask people that they have no difficulties in deciding what they should announce, they should just be truthful. Okay, so we want dominant strategy implementation. We want to design a mechanism so that they want to tell us truthfully exactly what their preference rankings are over the alternatives, and they don't gain at all by trying to mix up the alternatives and manipulate the system. Okay, so that's the idea. And in particular, let's think of, we've got our society with n individuals, a finite set of outcomes O, and if we begin to think about designing mechanisms in this world, and we want one where every agent has a dominant strategy for each preference, we can invoke the revelation principle. And the revelation principle tells us that if we do have an indirect mechanism that has dominant strategies, we can just collapse that into a social choice function, a direct mechanism, where people just tell us directly their preferences, and then we give them the outcomes they would have gotten through the original mechanism for each announcement of their preferences. So if they'd followed the strategies that they had dominant strategies in the original one, so this makes truth a dominant strategy. So the revelation principle means that we can, without loss of generality, for this exercise, look at social choice functions directly. Okay? And so now what we want to do is think about which social choice functions can a society have, which are going to be dominant strategy truthful in this sense. Okay, well, so it's these things are also known as non-manipulable, strategy proof. Sometimes they're called straightforward mechanisms or social choice functions. And the important result in this area, due to Alan Gibbard and Mark Satterthwaite in the early 1970s, is going to say we're going to have a really hard time doing this in a setting where people can have any possible ranking over the alternatives. So let's have a look at that. This is what's known as the Gibbard-Satterthwaite theorem. And it's another form of an impossibility theorem, similar to what we saw in terms of Arrow's theorem and the Muller-Satterthwaite theorem. So situations where we have a set of conditions we'd like to have, and the theorem says it's impossible to have this desirable set of conditions all at once. So what's the setting here? We've got a social choice function. We'd like to have one that's mapping all possible preferences. So people have linear orders. They can have any strict ranking over candidates. And we are going to look at situations with at least 3 outcomes. So we have at least 3 candidates to choose from. And we're going to also look at a social choice function which is onto. That means for every possible outcome, there is a profile of preferences which gives you that outcome. And that condition can be satisfied quite easily. For instance, if you just required that your social choice function be unanimous. So if all individuals prefer the same alternative, we all say we love candidate A, then society should pick candidate A. If you put that minimal condition in, then indeed in this domain of preferences, C is going to be onto. So if we put those conditions in, then what does the theorem say? The theorem says that we're going to have the strategy proofness condition, truthful reporting of preferences as a dominant strategy for every agent at every preference profile, if and only if C is dictatorial. Okay? So again, that means here there exists some particular individual I for whom the choice function is just always their favorite alternative, the thing that maximizes their preferences, and regardless of what anybody else says. So we just pick one individual, we just listen to that person. Okay? Now, in terms of the proof of this, it's clear that if we assign somebody to be a dictator and don't listen to anybody else, that's going to be strategy proof. Right? Nobody else can make any difference, doesn't matter what they say, and the person who is a dictator always wants to be truthful because they're getting their favorite alternative. The converse of this theorem is much more difficult, the part saying that if it's strategy proof, then it has to be dictatorial. And this can be proven by various means. There are proofs that relate this back to Arrow's theorem and show that there are similar conclusions it can get in terms of the basic steps, dilemmas that were proven there. There's a very elegant proof by Salvador Barbera, which works off of individuals being pivotal in terms of changing their preferences and changing the outcome, and showing that you can't have too many individuals being pivotal at once if you are going to satisfy dominant strategies. So there's a basic conflict of allowing people to make decisions and having multiple people make decisions at the same time, and making sure that everybody cannot manipulate things by announcing things falsely. So we're not going to explicitly offer that proof, but you can find various versions of this in the literature, and we'll leave you to look at that directly. What this means is that any social choice function that we write down that we're interested in, assuming that we don't want dictatorial functions, are going to be manipulable in some situations. So if we're in a voting setting and we have a set of candidates that we're looking at, and we have to pick among those candidates, and any possible ordering of those is possible in people's preferences, regardless of what rule we use, we're going to end up having people manipulate that rule in certain situations. So that's a very negative result in some sense. It's a damaging result, and it's different from Arrow's theorem, because what this is doing is really looking at the incentives that people have and saying it's going to be difficult to get people to be truthful. When we were looking at Arrow's theorem, there was nothing said about whether people were being truthful or not. The kinds of conclusions that were being reached in Arrow's theorem were just saying that some basic independence conditions and Pareto conditions couldn't be satisfied by a social welfare ordering at the same time, but presuming that you could see what people's preferences were as the input. And this is saying that if you're going to make a choice, it's going to be difficult to get people to reveal their preferences to you in a truthful manner. One more thing about this, and this is something you can verify yourself. Suppose that you only had two alternatives. Then it's going to be easy to find a rule. Think of majority rule. So is that strategy proof? So imagine that we have just two candidates and you get to vote for which one you would prefer, and you always prefer one to the other. There will be a variety actually of strategy proof rules in that setting. If C is not onto, then we are ignoring certain outcomes. Then you're going to have some more limited conclusions here that things are going to be dictatorial, but only on the range of the outcome function, if it still has at least three alternatives in it. So there's some limitations on this, but in terms of really getting around this kind of negative result, there's various ways we can think of doing this. One is to use a weaker form of implementation. So here we were asking for dominant strategies for all individuals at all preferences. We could work instead for something like Bayes-Nash implementation, Bayesian implementation, where we ask people just to have it be a best response to announce truthfully, given that everyone else is. And that'll open some doors for us. That's going to be much more demanding in terms of an equilibrium concept. And the beauty of dominant strategies is people don't have to worry about what other people are doing, and they don't have to know or have beliefs about what's going on. Bayes-Nash structure, a Bayesian-Nash structure, is much more demanding in that sense. We could relax the assumption that people have arbitrary preferences and look at more structured settings. And indeed, when we do that, we're going to find much more interesting and positive results in terms of rules that we can apply. So more interesting rules, I should say, not more interesting results. The Myerson-Satterthwaite theorem is a very interesting result. But we'll find more interesting rules that we can work with. We've already seen one, in fact, median voting on a single peak domain. So as we mentioned there, if you're asked for your preferences, you have no reason to try and distort your preferences. The median peak wins, and the only way to change that is to flip over and announce something on the other side, which would be worse for a given individual. You could also take the max of the peaks. You could do, instead of median voting, have maximum voting. So whoever has the maximum peak, or the minimum peak, or any order statistic. So single peak domains are going to be settings where what we've done is we've limited the set of preferences, so not any ordering over candidates is allowed any longer. And once you do that, then it's easier to design strategy-proof rules. Another setting, trade. So imagine that you have an indivisible good. You have a buyer and a seller, and they might have private values for how much they value the good, and you're trying to get trade to go on. One mechanism that works in that situation is just to fix a price. So say you can trade the price at a price of 10. So individuals say, at a price of 10, am I willing to trade or not? And now there's a simple decision. You can't influence the price. All you can do is influence whether you actually trade or not. And so then you have an incentive to say truthfully, do you really want to trade or do you not? And then trade if both of the agents want to trade. So there you can design a dominant strategy mechanism. There's going to be some inefficiencies associated with that. You're not going to have trade occurring in all the circumstances that you'd like, but at least you've got dominant strategies. And we'll take a closer look at these things. We're going to see a whole series of other types of rules. We'll look at the Vickery-Clark-Grove schemes and other kinds of schemes. And when we look and narrow in the kinds of settings that we're looking at with more structure on preferences, we'll have a whole series of interesting dominant strategy compatible mechanisms which are going to be present. And we'll take a look at particular kinds of environments where that's going to be possible. Will be next up. Okay, so we are now going to talk about a setting which will be analyzed quite extensively, basically for the rest of the course in terms of the types of mechanisms we're going to be looking at and the alternative games we're looking at. And in particular, what this is known as is a setting with transferable utility. And what's looked at in these settings are situations where people have what's known as quasi-linear preferences. And the idea, before we get into the formal definitions, is that there's something like money, some transferable good that we can move back and forth between agents, and we know how much that's worth to them, and we can trade that off versus utility. And that gives us a nice sort of private good that we can move back and forth, sort of payments in an auction or payments, contributions to a public good, and we'll assume that translates directly into some utility numbers. And the importance of doing that is it's going to give us a lot of power in terms of aligning incentives by making people's payments encapsulate the externalities that they're imposing on others in terms of decisions. So once we have transferable utility, it'll give us a lot of power in designing mechanisms in terms of making sure we basically can price everything, and we can figure out what kinds of prices people should be paying to change one decision to another decision, and that's going to be a very useful tool in designing mechanisms as we go forward. Okay, so what do the formal definitions look like? Instead of just having some abstract set of outcomes, now the outcomes are going to have structure, where there'll still be some basic sort of public aspect to it, some decision X. And then the other part is going to be a set of real numbers where we give each individual some payment or have them make a payment. So there's some transfers going on between the different individuals, and so we will have some list Rn of what those payments are. So in this particular setting, when we have quasi-linear preferences, so people have quasi-linear. So here, what we're going to have is things are going to be linear in this second dimension. So we can think of an outcome now as being a list of what's the public decision, some X and X, and then also some P, which is going to be a P1 through Pn of what those payments are. And a given individual's utility for the outcome can be split into a utility function which describes how they like the x's, and then also they subtract off whatever payment they're making. And that payment could be positive or negative. So it could be that they're paying something into the society as part of the outcome, or it could be that they're receiving payments. And these payments are going to be very important in designing efficient mechanisms, designing mechanisms to align people's incentives with what we'd like. Okay, so quasi-linearity gives us a lot of power. You can see where the quasi-linearity, where's the linearity part of this? The linearity part is that The preferences are always just moving linearly with whatever this payment scheme is, whatever the money dimension is. Okay, so when we start talking about mechanisms in this world, then we can split the mechanism into making a choice. So it's going to choose something. So I've got our outcomes are equal to x cross Rn. So what it's doing is it's first of all going to make a choice out of the x, and then also have payments in Rn. So x and x is a non-monetary outcome. And we'll use the term money here. It's not clear exactly what the transferable good is, but there's some way of moving something back and forth, which people can equate with utility. So there's some non-monetary outcomes. Often these are called public decisions, the aspect which is going to be common to all the agents. And then we've got these private payments where each person is making a payment into the mechanism. And if PI is negative, then that means they're actually getting a net payment to them. And the implications in terms of making this kind of assumption in terms of these preferences, first of all, the utility that somebody has for this outcome can be separated out from the utility that they get from the payment. So it's not influenced by the amount of money or wealth an agent has. And secondly, people care, a given agent cares only about X and their payment PI. They don't care about, say, PJ where J is not equal to I. Right? So they don't care what payments other people are making. They just care about what's the overall decision, which candidate do we pick, or which public good do we pick, or what decision are we making in terms of who gets what good, and then what payment do I have to make. And I don't care what other people's payments are to the extent that it doesn't enter into my payment. Okay, so that's the setting. And then a direct mechanism in this world is going to be a combination of some choice, some x theta, which comes out of x, and a payment scheme as a function of the thetas. So now we announce our thetas, and then society spits back at us a public decision, this non-monetary decision, and then a list of transfers or payments that we're each going to make. Okay, so that's a direct mechanism. One thing that's going to be very useful in these kinds of settings, and a lot of the analysis that we do going forward will be in a special case of quasi-linearity. And when we're thinking about the utility that individuals have, so now we're writing people's utility overall as a utility of what the x is and the theta minus pi of theta, right? So, and this x can depend on theta. What we're going to do now is we're going to make a look at situations where there's a further assumption made, where instead of having people's preferences depend on the full vector of types in the society, it's going to depend only on their own type. So we'll say that preferences have private values or satisfy conditional utility independence if a particular person I's utility function depends only on theta I. Okay? So the utility for this overall outcome does not depend on anybody else's type. It only depends on my own type. So that means that once I know my own theta, I know everything about my preferences. And what this rules out is things like investing in a stock where I'm not quite sure what the value of that investment is. I don't know how well it's going to pay off. And other people might have information that would be very valuable to me. That's ruled out here. Once I know my information, I know everything I need to know about my preferences, and nobody else's information enters into that preference calculation. Okay, so if we're talking about a particular candidate, I know whether I like this candidate or not. Or if it's a public good, I know whether I want that public good bill. So what's nice about the private good setting is now instead of just thinking about theta i's, we can think of just people just telling us what their utility function looks like. So we can think of the private information they have is just a valuation function, vi of x, which is equivalent to this ui of x of theta I. So the theta just becomes telling us what that function is. Okay, so agents have a valuation function, which is basically the value that they have of any particular allocation x. Okay, and so then when we start thinking about direct mechanisms, we can think of the space of individuals that the private information individuals have as these VIs. So in particular, everybody can tell us instead of a type, they tell us now their valuation function. And the standard notation we'll use is that people will tell us some v hat I, which might be a lie. I mean, so dominant strategy mechanisms might not always exist. It could be that people are going to tell us some alternative valuation function instead of the true valuation function. And so we can look at when is it that they're going to want to tell us their true valuation function. So now we ask people, how do you value these different alternatives? And under this private value or conditional utility independence condition, they know their own preferences, and they can tell us what that preference function is. And then we can look at mechanism design and ask it, when is it that possible in now this quasi-linear world with these private values to get people to truthfully tell us what their preferences look like.
Hi all, it's Matt again. So let's take a look at an example which will illustrate some of our transferable utility mechanisms. And in particular, let's think of a fairly canonical example where we've got a set of citizens and they're trying to make a decision between either undertaking a project or not. So this might be, say, building a library, building a new school, making some sort of investment. If it could be a club deciding on making an investment of some kind. So there's a set of people, and we'll keep track. So N is just our set of individuals, and now the outcomes we'll just keep track of as either 0 or 1. So 0 means status quo, you don't do anything. 1 means you undertake the project, make the investment, and so forth. And so the idea now is that the types represent somebody's private value in this particular example for the two possible options. So this is a valuation function. So basically they have utilities for doing nothing and utilities for undertaking the project. And undertaking the project is going to involve possibly, some taxes and other kinds of things and maybe benefits. So each person has a utility of doing nothing and then a utility for what happens if they undertake this investment. Okay, so for instance, one possibility is that somebody has a utility of 0 for doing nothing. We can normalize it to 0. And then if they undertook the project, this is a person who likes the project, they would get some 4 utils for doing this. So given that VI of 0 is 0 and VI of 1 is 4, we can just represent that by a vector 0, 4. So we could say that person has a vector of utility 0, 4. Okay, another possible utility, maybe there's somebody who doesn't like the project. That type could be represented by a 0 and a -2. So what this does is it keeps track of how much each person values not doing the project, how much they value doing the project. And so now a person's type is just represented by these valuations. And these valuations can be thought of also as transferable in the sense that we can just pay them to compensate them. So if you wanted to compensate this person down here for the pain that they're enduring for building this thing, you'd have to pay them 2 utils in order to make them happy if you undertake this. This person would be willing to pay up to 4 utils to have the project built. Okay. So in this kind of mechanism, now we can think of this as a direct mechanism. People are going to announce their types. So for instance, if we keep things simple and they're either types who like it and get 4 utils for it or don't like it and get -2, then there would be 2 possible type vectors, the 0, 4 type and the 0, -2 types. In general, you could have lots of types, but for this example, let's just keep it simple. And one possible mechanism would be to say, okay, look, if a majority of people announce 0, 4, if a majority of people like the project, then we'll build it. If a majority of people don't like the project, we won't build it. So we'll just take a majority vote, and then we'll build it or not. So in terms of our notation of a mechanism, if a majority of people announce the 0, 4 types, then X, the outcome, is going to be 1. You undertake the project. And if we're not doing any compensation, then everybody gets a PI of 0. So basically, we just go ahead, we undertake the project, and there's no transfers or subsidies back and forth between individuals. In contrast, if the majority of people announce 0, -2, then we don't undertake the project, and everybody ends up, again, with a payment of 0. So this is a simple example, just a straight majority vote over the project. What's interesting about this mechanism? Well, it's actually a dominant strategy in this particular example to announce your type. I'm better off voting to not get the project built if I don't like it, and voting for it if I do. So truth is in equilibrium. But sometimes, what are the downfalls of this? Sometimes some of the people get negative utility. So sometimes the project is built and there's a bunch of people getting -2s. And also the choice doesn't maximize the total utility in a society, right? So this mechanism isn't good in terms of maximizing the total utility. It's not accounting for the fact that these people like it twice as much as these people dislike it. So one possibility would be to say, okay, look, let's try a different mechanism. Why don't we try, instead of having a majority, if a third of the population likes it, then we'll go ahead and build it. So now we're trying to do something where instead what we take into account is these people like it twice as much as these people, so we'll weight their votes twice as much, and we only need a third of the population to announce the V hat types, the 0-4 types, in order to have the project undertaken. So we could change that mechanism, right? So now, again, people announce their types. And now if the number of people, let's let M be the number of people who have voted for it, so the 0-4 types, if that's bigger than a third of the population, then we go ahead and undertake the project. But now what we're going to do is we're going to try and also compensate the people who don't like it, right? So there's a bunch of people suffering for it. So what we'll do is the people who announce the positive, so they're the people voting for the project, they're going to have a payment that they have to make, which is going to be n minus m over m times 2. That's going to be enough to cover the payments that we make to the n minus m other people who are voting against the project. And those people will receive 2 payments. So this is a mechanism where now we're allowing the people who are for the project to have a stronger vote, but then we're going to compensate the people who have pain inflicted on them. And otherwise, if we get too few votes for it, then we don't build the project and we don't make any payments. Okay? So this is a mechanism which now is making the choice that actually is best for society in terms of the overall maximization of total utility. It's also one that compensates the people who are receiving pain for it. What's the difficulty with this project, this particular mechanism? Well, the problem with this one, it does maximize total utility. You never get a negative utility, but now we've lost the fact that truth is in equilibrium, right? Why have we lost the fact that truth is in equilibrium? Well, let's suppose, for an example, think of a really, really large society. And suppose you're a type that is a 0-4 type. And suppose that, for instance, there's half of the people who you think might like it, half might not like it. Well, if we have a really large N and everybody else is honest, then the chance that my announcement is going to make a difference in the undertaking of the project is really vanishing. So the larger the society is, then the chance that I have an impact on the vote, for instance, if people's types are drawn independently, it becomes really tiny. And so then all that happens is now my type is going to affect my payment, right? So it affects whether I'm making a payment into the system or getting a payment out. And we're going to lose truth as an equilibrium because I realize my vote's not going to make a difference. Now if I'm a 0-4 type, maybe I pretend to be a type who's receiving pain from the project so that people make a payment to me instead of me having to make a payment in. So you can begin to see that different mechanisms in these kinds of settings are going to have very different properties. Some of them might be good in terms of truth. Some might be good in terms of maximizing overall utility. Some might be good in terms of compensating people, balancing so that payments are balanced across the society. There's going to be a whole series of different conditions we're interested in. And the question is, can we find mechanisms that are going to have nice incentive properties, nice efficiency properties, and nice balance properties and so forth? Can we get all of those at once? And we'll take a look and see that some mechanisms come pretty close to doing that. It's not always possible to get everything, but in a lot of contexts, we'll have mechanisms that do pretty well.